All right, think about this for a second. You push a quick hotfix to prod. You hit play on that new show everyone's talking about. Or you just drop a meme in your group chat. Every single time you do that, there's this incredibly complex dance of data packets happening across the globe. And it's all orchestrated by one thing, TCP/IP. It is literally the engine of the internet. But for a lot of us, it's still a complete black box.
So, to get us started, let me throw a puzzle at you. We all know TCP is the gold standard for reliability, right? It's the protocol that makes sure every single bit of a web page gets to you perfectly. So, why is HTTP 3, the future of the web, being built on its kind of reckless, unreliable cousin, UDP? What's the deal with that? Just keep that question tucked away in the back of our mind as we go.
Because that's exactly what we're here to do. We're going to pop the hood on the internet's engine. It's time to stop treating this fundamental tech as some magical black box. The goal here is to give you a really clear, powerful mental model of how it all actually works. All right, let's get into it.
So, let's talk about the big picture, a 4-layered blueprint. You can think of it as the Lego bricks of the internet. See, before TCP/IP, networking was a total mess. It was chaos. Imagine every company making their own Lego bricks that didn't fit with anyone else's. You couldn't build anything together. TCP/IP came along and changed all that. It standardized the bricks, creating this universal blueprint so that any device, anywhere, could finally connect and, play nicely together.
Okay, so what is it exactly? Well, TCP/IP, that's Transmission Control Protocol/Internet Protocol, is basically a set of rules. It's a suite of protocols that lets everything, I mean everything, from your phone to a giant data center, speak the same language. It's the universal translator for the internet. It's what dictates how data gets chopped up into pieces, addressed, sent across the world, verified, and then put back together perfectly on the other side.
And the real genius of TCP/IP is its layer design. It's broken down into these 4 distinct layers: application, transport, internet, and link. Now here's how it works. When you send data, it travels down this stack. And when you receive data, it comes back up. This separation is absolutely key. Why? Because it means you can say swap out your Wi-Fi for a physical Ethernet cable down at the bottom link layer, and your web browser at the very top doesn't even know or care. It just works. It's brilliant. All right, so let's follow a piece of data on its journey. We're going to start at the very top with layers 4 and 3, where the data is actually generated and prepared for transport. This is where the journey begins. Okay, the application layer. This is your world. It's where all the protocols you actually interact with live. Think HTTP for your web browser, FTP for file transfers, DNS for looking up websites. The job of this layer is super simple. It just creates the data. It figures out what you want to send, and then it just passes it down to the next layer to worry about how to get it there. Now we're at the transport layer, and this is where a really important choice happens. It's reliability versus speed. You've got 2 main options. First, there's TCP. Think of TCP as the super reliable, detail-oriented courier. It establishes a connection, guarantees every single packet arrives, makes sure they're in the right order, and even slows down if there's traffic. Then you have UDP. UDP is different. It's the fire and forget option. It's connectionless, it just sends the data and hopes for the best. No guarantees. So of course, for something like loading a web page, you need TCP. But for a video call, a tiny drop frame is way better than a huge lag. So you go with the speed of UDP. So how does TCP pull off that incredible reliability? Well, it all starts with something called the 3-way handshake. It's basically a polite little conversation before any real data gets sent. First, your computer sends a SYN packet, which is like saying, "Hey, server, you there? Want to talk?" The server responds with a SYN/ACK, saying, "Yep, I'm here, and I'd love to talk." Finally, your computer sends back one last ACK, which just means, "Awesome, let's do this." Only after all that is a connection established and data starts to flow. It's rock solid for sure, but think about it. That's a whole round trip across the network before you've even sent a single byte of useful information. That's the price you pay for being so reliable. So to sum up the transport layer, think of it as the project manager for your data's journey. Its first job is to pick the right delivery service, the reliable sedan, which is TCP, or the super fast motorcycle, UDP. And its other crucial job is to use something called ports. A port is like an apartment number. Your computer has an IP address, which is the building's street address, but the port tells the data exactly which apartment or which application to go to inside that building. And a perfect example of this is port 443. Whenever you visit a secure website, one with HTTPS, your browser sends its request to port 443 on that server. That number is a universal signal that tells the server, hey, this incoming data is for your web server software, not your database or your email server. It's a really simple but super effective way to handle tons of different conversations at the same time.
Okay, our data is all packaged up by the transport layer. Now for the fun part, addressing it and actually getting it delivered. We're heading down to layers 2 and 1, the internet and link layers. This is all about how we cross the actual network from point A to point B. And the absolute heart of the internet layer is the IP address. It's so simple, but so powerful. Just think of it like this. Every single device connected to the internet has its own unique IP address. It's a phone number, a postal address. It's the unique identifier that tells the entire network exactly where to send the mail. So yeah, this layer is basically the world's biggest postal service. It's responsible for that global addressing and for routing packets across all these different networks. But here's a really critical insight. The internet protocol itself is, well, it's deliberately simple. It's best effort. It doesn't guarantee anything. Not delivery, not order, nothing. That's TCP's job, way up in the transport layer. All IP does is look at an address on a packet and forward it one step closer to its destination. And by keeping the core of the network simple and fast, it allows the whole system to scale massively.
Okay, so you might be wondering, when a computer receives one of these IP packets, how does it know what to do with the data inside? How does it know to give it to TCP and not UDP? Well, right there in the IP packet's header is a little number, the protocol number. If that number is 6, the computer knows, this payload goes to TCP. If it's 17, it knows to send it over to UDP. It's just another one of those tiny, elegant details that makes the whole system work.
And at last, we've reached the bottom of the stack, the link layer. This is where the digital world meets the physical world. This is where the rubber really meets the road. This layer takes our neatly organized digital packet and turns it into actual physical signals. Electrical pulses down an Ethernet cable, radio waves for your Wi-Fi, or flashes of light in a fiber optic cable. This is the nitty-gritty physical transmission of raw bits.
Okay, we've looked at all the individual layers. Now let's put it all together and see how they work in perfect harmony. We'll trace the anatomy of a simple web request from start to finish.
But before we do that, we need to understand one more crucial concept: encapsulation. It sounds complicated, but the idea is simple. Think of it like Russian nesting dolls or a series of nested envelopes. As your data travels down the stack, each layer wraps the data it receives from the layer above inside its own envelope with its own header information. So your HTTP request gets put inside a TCP segment, which then gets put inside an IP packet, which finally gets put inside an Ethernet frame. Each layer adds its own address and instructions.
Okay, here we go. The entire journey of a web request. 1. You type in an address. Your browser, up at the application layer, uses DNS to find that site's IP address. 2. The transport layer kicks in. Your machine does that three-way TCP handshake to open a reliable connection to the server on port 443. 3. The application layer creates the HTTP request, and it gets encapsulated as it goes down the stack. 4. Now we're at the internet layer. Routers all over the world start forwarding these IP packets, hop by hop by hop, towards their final destination. 5. The link layer does its thing, and the packets physically arrive over your Wi-Fi or your Ethernet cable. And finally, 6. On the other side, the whole process happens in reverse. The layers are unwrapped, TCP perfectly reassembles all the pieces in the right order, and bam, the web page appears in your browser. It just feels seamless.
So we've unpacked the black box. We've taken a look at all the gears and levers inside. But so what? Why does any of this actually matter? Why should you care?
Well, because this stuff isn't just abstract trivia. It's incredibly practical. When your API call is timing out, is it a DNS problem, a TCP handshake issue, a routing problem on the internet? Understanding these layers lets you debug network issues like a pro. It helps you build more resilient, more performant systems. And, maybe most importantly, it gives you the foundation to understand why new protocols are even being created.
And that brings us right back to the question we started with. Now that you understand the awesome power and reliability of TCP, but also the cost of that three-way handshake and its super strict in-order delivery, why on earth would the future of the web, HTTP/3, be built on the unreliable UDP? The answer has everything to do with getting around TCP's rigidity in a world of multiple simultaneous streams. But hey, that's a deep dive for another day. For now, it leaves us with a fascinating question to think about. In the quest for a faster, more responsive internet, what trade-offs are we willing to make?